In order to understand the basics of circuits, there are four things I want to look at today. The first one is that you come away understanding what voltage is as it pertains to a circuit, what current is as it pertains to a circuit, and what resistance is as it pertains to a circuit. So these are three of pretty much the four major things we're going to be looking at when it comes to circuits. So I just want to make sure you understand the very basic idea behind each one so we can move forward in our analysis of circuits. And I'd also like to make sure you understand how batteries work because we're going to basically power the circuits that we take a look at. So if we can come away with a better understanding of these four things, we're going to be in a good position moving forward. The first thing I want to discuss is voltage, which we've kind of discussed as it pertains to a field. So I'm going to quickly review that. So one of the things we want to talk about is if I have like an electric field between two plates, positive and negative, if I look at this point here, we would say to ourselves that this is a region of space that a positive charge, would not want to be placed in. Remember, there's nothing here, but we would say that this is a high voltage region because it's a region of space in which a charge would not want to find itself, meaning any positive charges that I do eventually place here will have high energy. And what we would say is this point down here, because this is a region of space that a positive charge would like to be in, we say that this is a low voltage region. In circuits, what we're more concerned with is not necessarily the voltage at a specific point. We're a little bit more concerned with what we call the potential difference or the voltage difference. So you'll see quite commonly this written as delta V. It's the change in voltage between those 2 points. And the reason we want to just kind of understand that is if I put a positive charge here, it is naturally going to want to move in this direction. So it's naturally going to want to move to a lower energy state. And when I allow that to happen, this change in voltage is related to the energy that is lost here. Because a positive charge moving in the direction it wants to go will lose energy. And it's this change in voltage that pertains to that change in energy. And that's what's going to be the energy that powers whatever devices we plug in. So just a quick recap, just to understand voltage, remember, is kind of, it's the energy rate at which a charge will gain potential energy when placed at a location. So it's basically the difference in energy rates between two regions or two locations. So if I were to take a look at this region and this region, we can make a general statement. Any positive charges moving from this region to this region will give energy away. And that energy is what powers our circuit. More commonly, you'll see me referring to what I call the waterfall analogy. So the waterfall analogy is nice in the sense that we all kind of have an idea of what happens with the waterfall. The water will fall down and continue down the rest of the river. Well, the voltage is provided by either the wall outlet or the battery in our circuit. And it's just important to understand that in the waterfall analogy, the height of the waterfall, that's kind of what relates to the voltage in a circuit. So if we just look at the height of this, we can kind of imagine that the higher this waterfall is, the more powerful the water is going to be rushing down, the less likely you're going to want to be standing right here. If it's a very high waterfall, there's going to be a ton of energy by the time the water hits the bottom. If it's a smaller waterfall, there's less energy here. So the thing to just realize is that voltage in your circuit is basically, in this analogy, it's equivalent to the height of a waterfall. So the higher the waterfall, the more powerful or the more energy the water has when it hits the bottom. Just like the bigger the difference between these 2 points, the more energy those charges will have as they move between them. So a higher waterfall is kind of like using a higher voltage battery. So just as we move forward, I'll keep connecting to this. But just understand the voltage is basically kind of what powers your circuit. The difference between those two terminals, whether it be a battery or the 2 prongs and an outlet, that's what's going to cause those electrons to move. Just like the higher the waterfall, the more that water is going to free fall and the more energy it will have when it hits the bottom. The second thing is the current, and that is also, again, related to the voltage. So you have some difference between like the negative and the positive terminal of the battery, let's say. So we have electrons that want to move from the negative to the positive naturally. If it's a big potential difference, if it's a big voltage difference, then we're imagining a very high waterfall, and those charges will flow faster. So if we want to measure current, we just look at any given point, and what we would do is we would figure out how much charge passes through in a given amount of time. So if you really think about it, it kind of makes sense. Just like if we wanted to measure the current in the river, we would stand here and we would take a look and we would see how much water rushes by us in a given amount of time. Same thing. How many charges rush by us in a given amount of time? So current is measured in a unit called amps, which stands for ampere. We'll usually just use an A, or we'll say amps, but it is technically amperes. And it measures just the rate at which those charges are moving by us. All right, so at any given point in the circuit, if we just basically count how many coulombs of charge pass by in a given amount of time, that will tell us the current. So more charges moving through in less time means a high current, and few charges moving through over a long amount of time tells you it's low current. So in the waterfall analogy, as I kind of already touched upon here, the rate at which, like if I were to look at this point here and I were to only count the water that flowed through this point, if I only count the water that flowed through this section over a given amount of time, well, if I took the charge, or I'm sorry, if I took the current of the water and I divided it by the time that passed, I'd be able to get that current. So the amount of water that flows through a given section in an amount of time we call current. The amount of charge that flows through a certain point over a given amount of time we call current as well. Just to make the connection, as we said before, that voltage is kind of like the height of the waterfall. Well, the higher the height of that waterfall, the faster water will be flowing through a given section. So just like the higher the waterfall, the faster the current, and the lower the waterfall, the slower the current. The higher the voltage, the faster the current in the circuit, and the lower the voltage, the slower the current. So like I said, just going to keep making those connections back and forth. The last thing we want to discuss would be the resistance. Resistance we measure in what are called ohms. And we have this kind of weird little horseshoe omega symbol. So you'll see either one of those. And resistance is just the natural impediment or the natural resistance to the flow of charges that various materials have. So if we had a circuit here and we had a voltage difference, so we had some difference between these two terminals, charges are going to want to flow from the negative to the positive side. So given any point, we can count the charges passing through a given amount of time, and that will give us the current. So we have the voltage source, we have the current. So the last step is the resistance. Now what I've drawn here, these little squiggly lines, those are what we call resistors. Those are just some kind of materials that will try and prevent the flow or slow down that current. Now, what are these usually? These are things maybe like a television, maybe this is like your phone. These are just whatever devices you plug in order to charge them up, because as they slow those electrons down, they take that energy and convert it to something else. But this is basically anything you plug in. A resistor could be a microphone, a television, a phone, a laptop, and literally anything you plug in. A light bulb is going to be a resistor. It's going to be anything that naturally slows down the flow of that current. Now it slows the current down, it converts that energy into, let's say, sound and light, and heat maybe. If you are using an electric stove, it converts it to heat. If you're using a fan, it's going to convert it to kinetic energy. So in the waterfall analogy, we already know that the voltage is the height of that waterfall, and that relates to the current, how quickly that water or those charges are flowing by. Well, in that example, our dam here that slows down the current or attempts to slow down the flow of that water, that would be a resistance example or our resistor. So by slowing down the flow of that water, it's converting that energy into something else. So maybe this dam would be connected to like a hydroelectric plant, which would then send out the electricity. It could be a variety of different uses, but just like a dam uses the slowing down of that water to pretty much convert it to electricity, it converts the energy into something else. So there's a few different variables at play here, right? The height of the waterfall is like the voltage. That relates to the current, how quickly the water flows. And the resistance has to do with how quickly or how aggressively you slow down that current, and thereby converting its energy into something else. So if I were to remove this dam, the water will flow faster. If I were to add a second dam down here, that would slow the water down further, because when I increase the resistance of anything, it's going to be harder for things to move through that. So the big concepts that I'd like you to take away would be the idea that voltage is the difference between the energy rate of 2 points that powers a circuit. So the voltage of a battery tells us what the difference between the two terminals are, and the bigger that difference, the stronger the flow of charges will be. The actual flowing of those charges is known as current. So if I want to know the current, I count how many charges pass by over a given amount of time, and that will give me my current in amps. Resistance is the natural impediment or resistance of a material to the flow of charge. it takes those charges, it slows them down and converts that energy into something else. And just realize with the waterfall analogy that these three all relate to one another. So the height of the waterfall, that's like the voltage. All right, the higher the waterfall, the more energy those charges will have. Let's go ahead and close this. Move it out of the way. So the higher that is, the stronger the flow of the current will be. And if I want to throw things in the way, like resistors or dams, that will slow down the current, and that will allow me to convert that energy into something else. So these three are very closely related to one another. And we'll take a look over the next week or so about how they specifically relate to one another. But if you understand these basic terms and you think you'd be able to identify them and maybe use them in the waterfall analogy, what we do moving forward should be a little bit easier.